So, I didn't show the channel coding film, like the proof for channel coding film yet. Uh, to do that, I need to digress a little bit, like only a little bit. So to talk about a couple concepts, like one is a Johnny typical. So we already talked about typical sequences. So Johnny typical is just an extension for that. So Johnny typical sequences, it's like if you consider, remember, like just a like we call here, like for typical sequences, I have some source here. So we say like essentially, if you look at a sequence drawn from this source here, like x1, xn, let's say, um, I know that like this sequence will always have like the probability to converge to like this like px, or like maybe I write pxn here, to converge to like 2 to the nhx to the minus nhx. And we say that like when this happens, basically like when pxn is less than equal to 2 to the minus nhx minus epsilon and 2 to the minus nhx plus epsilon. So we say that this xn is typical. And essentially, this is like just by law of large number. If you pull a sequence from this source, it's always, almost always, like, it will be typical. So now an extension is I will consider joint source. So we have like pxy here. So we consider a pair like x and y. Kind of like we're going to draw like a pair of uh, kind of like a pair of like random variables from this source, like and drawn a sequence like x1 up to xn, like y1 up to yn. So we say like this x, let's say xn, yn to be Johnny typical, denoted by notation like that, xy. So if basically x is typical, xn is typical, and also yn is typical, and also like we have similar to something like that, like p xn yn is less than equal to um, minus n h xy minus epsilon is like to the minus n h xy plus epsilon. So if that's the case, this is Johnny typical. And basically, like, by law of large number again, like, if you're going to pull sequence from this source, essentially everything you pull from this sequence, from this source, will be Johnny typical. So then we can basically essentially use a same argument as what we did earlier, like several lectures before, uh, to find the number of Johnny typical sequences, and also like yeah, basically what's the size of the Johnny typical sequences, like number of Johnny typical sequences will be approximately just like 2 to nhxy. So essentially, because like if you think of that, each of that have like same probability, approximately 2 to minus nhxy, and every time you draw from this, it has to be Johnny typical. So therefore, like if you sum up all these sequences together, the probability should be equal to 1. So therefore, the number of these sequences to be 2 to the nhxy. So you can give a more rigorous proof, but yeah, essentially like the number of sequences 2 to the nhxy. And yeah, I maybe I can give a more tight, kind of more precise bound here. So I have like will be less than 2 to the nhxy plus epsilon, I guess, and this is less than equal to let's see, I think I have some delta here, 1 minus delta 2 to Yeah, this delta, don't worry about that. But like there will be have like some kind of bound like this, as it would be like the size of the joint typical set, the number of joint typical sequences. Now, why we like to talk about joint typical sequences is that we're going to use that like to construct a decoder for our channel coding scheme. I mentioned earlier, like at the beginning, what Shannon did is like really ingenious. Like he didn't really create a concrete kind of coding scheme for the channel, but instead like he just think of a random code, um, random random code. It's a random coding argument, and then like he create a decoder. Essentially, the decoder is very simple. He think of like, okay, I have like some xn here. It's going to send through the channel. Then I have the sequence yn, right? Now, how it's going to decode it is like, if you think of like there's many cohort here, xn1 up to xnm here, let's say like m cohorts here. Um, how it's going to decode it is like it's going to see like whether he can find one of them is jointly typical with yn here. So the decoder is basically to decode, uh, find m, let's say that this is big M here, find m such that xn m and yn are jointly typical. So if I find this n, then I output m as decoding output. Yeah. So basically, like, okay, I was just trying to find whether like one of them will be jointly typical with that one, that y output of the channel here. If I have one of them, one of the cohorts jointly typical with yn, then the corresponding index of that cohort m will be basically the message, the decoder message. So it's very simple idea. Now, but to analyze that, like we need to consider a couple of things. Then first I will probably like this will be the last thing I'm going to talk about today. Today is a packing lemma. So one thing we will consider is that if you look at that, look at the slide earlier, look at the page earlier here. So when I was going to have like trouble like decoding this message here, so that will be like two kind of errors. Like error one will be, okay, I send actual message, I say is m. Let's say like I find m hat is like the m hat is like going to be Johnny typical with yn or something like that. Okay, first error message is like I have this or okay. For yeah, that probably like more than this different kind of errors. But let me put in these two errors. Like these two errors can cover essentially all the errors. So first error is like I cannot find any of this cohort here is jointly typical with xn. Uh, no xn m hat yn are jointly typical. So if this happens, basically the decoder fail, right? So it cannot find a cohort that is jointly typical with the output of the channel. It doesn't know what to do. So then it's like just hangs there. It doesn't can do anything. Now the second case is actually going to be the more interesting case. It's like um I have like m hat is not equal to m, but x n m hat and yn are jointly typical. So if I have like m hat is not the correct one, so it's like jointly typical with ym, then I of course I would decode error, I have to get one error because I may output like m hat as the output instead of m, right? So I would think that it's actually sent m hat instead of the original m. Now, what the packing lemma does is I want to analyze something like that. So you see that like this error will increase. Like I will have more higher probability of this error if I pack more of this message here, right? So if I have more M here, I mean, if M bigger, error event 2 is more likely, right? My handwriting, so sorry about that. So if I have a bigger M, I have more message. It's more likely that like I have this uh, chance to get an M hash that's not equal to M, but it's just Johnny typical with YN, right? So packing lemma, like basically now packing lemma. So what packing lemma want to ask is like how many xn, actually independent xn, can we pack with yn such that x and yn are not Johnny typical, or maybe like are not Johnny typical. So for all, maybe I write this like or m. So maybe I have like m messages, one up to big M here. Like how many m, how many like messages I can pack, or like how many different xn I can pack with yn, such that none of them are Johnny typical with yn. So that's the question here. And it turns out the result is like the answer is like 2 to the sorry, answer is like m is less than 2 to the n I x y, something like that. So and we are going to show this like very quickly. I'm not sure, like 3 minutes would be sufficient, hopefully. So what I'm going to do is I first assume like I have m messages, like m messages, and then like if I, what's the probability like any one of m xn or Johnny typical with yn. So the probability for that will be less than a, because each of these of them are independent, right? Each of these xn are independent, right? Will be just equal to the um let's see, will be less than equal to the m times the probability of like each individual of them xn yn to be Johnny typical. Let's see. Yes. And probability that like any one of them to be Johnny typical. Oh, wait. Will be equal to, okay, I probably need to extend it. So, oh, okay, I didn't have this result yet. So this probably will take me more than 1 minute. So this one actually turns out will be equal to 2 to the minus nixy, but I will list a few steps for that. So therefore, if you look at that, then okay, I probably like need to delay it to next time. Okay, actually after the midterm. So, but yeah, this one, if you elaborate a little bit, like actually it's probably not too hard to see because like this, yeah, I guess like that's still like too many steps. So But if I know this one is equal to 2 minus n xy, then like this m here, I can write it as a 2 to n r, um, represent as 2 to n r, and then I have 2 to n r minus ixy. So then I will basically have like, as long as r is see, yeah, r is less than ixy, then less than equal, basically less than ixy, then I will have like this converge to 0. So then I will have like none of them is going to be like jointly typical with yn. Okay, but anyway, I guess I probably need to repeat this part next time. So I mean after the midterm. So okay. Uh Ask me questions like on Discord, like if you have any question regarding to the test midterm. And yeah, please, if you didn't submit, still submit your homework, please do it like as soon as possible. And as I said, like once I receive your assignment, I will try to like send out the solution to you like by email. Okay, so that's all. I'll see you guys. Like, okay, good luck with your midterm. Oh, and by the way, like for any of you want to, I know Richard is need another day. So if like some of you guys, I assume you guys are not going to cooperate somehow. I don't see that's incentive like for you guys. For example, like some who take the exam earlier and share the exam to others. I don't see why you want to do that. So if you have any particular reason you need to do the exam a bit earlier, like or some other time, like I can yeah, I don't see there's any reasons I cannot accommodate that. But you need to let me know. So but it shouldn't be like, for example, like too far away. For example, like within 24 hours, like one day, like within one day or so. Like for example, if you want to do it one day earlier or like one day later or something like that, that should be fine. Yeah. Okay. So I will see you guys then.